So, what we want to look at today, since we did the test yesterday, is we want to look at formulas that are specific for each of your programs that involve the stuff we've been talking about. A big one for telecom or broadband is electronics. When you're dealing with electronics, if you have an AC circuit, and that's just the symbol I use for an AC voltage source, with a resistor and an inductor in it. Let's say our voltage source is 60 hertz, standard electrical cycle. We have a resistor of, let's call it 4.5 kilo ohms, and an inductance, let's call it 5 Henry. The inductive reactance is found. X with that L by little sub L is inductive reactance. It is found as 2 times pi times the frequency times the inductance of that inductor. So the inductive reactance here, 2 times, we're going to go 3.14 times what's F? 60 hertz times what's L? That's the 5 Henries. I don't know why I put I there. That should be an L. So that's times 5. So we have 2 times pi, 3.14, times 60 times the 5 Henry is 1884. That is in ohms as reactance. It's similar to a resistance. To find the total impedance of the circuit, then, we add that to our resistance, but we have to add it in a special way. It's called phase shift. Our resistance is at 0 degrees, and we'll talk. This will make a little more sense after we do some trig in the spring. The inductive reactance is at 90 degrees. The total resistance, total impedance of the circle, or of the circuit, not circle, is that amount right there. We can think of it as being the diagonal distance across that rectangle. Well, how would I find that length? Well, we know that R is 4,500, 4.5 kilo, right? Ohms. And we know that XL was 1884 ohms. So this distance across here, that's basically a right triangle, isn't it? So it's A squared plus B squared equals C squared. The total impedance of that circuit, Z squared, is equal to the resistance squared plus the inductive reactance squared. So Z squared is 4,500 squared plus 1884 squared. Now, what I normally do is I punch this in the calculator all as 1. So I just do Z equals the square root of 4,500 squared plus 1884 squared. So if you punch that in, second square root, 4,500 x squared plus 1884 x squared, we get 4878.5, we'll call it. That is the total impedance of that circuit. Now let's say our voltage source is 120 volts. Again, helps to put the 0 in there. 120 volt voltage source. Have you guys covered EMF and RMS? Okay. So that's obviously 120 volt RMS, average voltage. The current is that voltage divided by that impedance. So 120 volts divided by 4878.5 ohms. I'm just going to do this since it's already in my calculator. We'll do 120 divided by that previous answer. So I get 0.0246, we'll call it. Amps, otherwise known as 24.6 milliamps. Does that make sense? Okay, I'm going to give you guys one to work on here quick. Then we're going to talk to Woods for a little bit. So this is still 60 hertz. The resistance, let's go with just 3 kilo ohms. And the inductance, let's go with 3 Henry. I want you to find XL, the inductive reactance. I want you to find Z, the total impedance. I'll put ZT, total impedance of the circuit. And for E equals 220 volts, find the total current in the circuit. I'm going to give you guys a second to copy that down, and we're going to do some examples for Woods so you guys work through that. By the way, in your little book, Unit 38, these formulas are in there if you didn't get them all written down. You have them? Okay. Get the circuit down? Good? Okay. For Woods, you guys have a lot of formulas that you use. First one I want to look at, we're going to talk about sheeting the outside of a house right now. What's that? Sheeting a house. For looking at sheeting a house, there are really two pieces that we're going to deal with. Let's say we've got a house that's 32 feet by 44 feet, and we want to sheet it. If we're looking at the outside of this, we can cut it up and we can unfold it kind of like we did with that lateral area. You've got the end piece there that's 32 feet. Then you've got the side piece of 44 feet. You got another end piece of 32 feet and a side piece of 44 feet. Now the total height of that, assuming, let's say that there's 8-foot interior walls, which is what we're going to assume is 8-foot interior walls. The outside height is going to be approximately 9 feet. So we're going to use this 9-foot height for the outside wall. Why is the outside wall higher than the inside wall? Well, the biggest thing is the floor thickness, right? You have to sheet across the down below the floor joists. Wow. Now we know the floor joists are more than a foot thick in most cases, but also usually with the way your trusses, your overhang on your trusses comes below the top of the wall. So the top 3 or 4 inches of your wall are usually blocked by trusses. So you don't have to sheet all the way up to the top of that exterior wall. What's missing in my picture here though for area that I need to sheet? It would be here and here. There you go, the gable end. So for exterior wall sheeting, what we're looking at is this dimension here, which is just the perimeter of the house, right? That is what, 76 times 2, 152 feet is the perimeter of the house. Times that 9-foot wall height. So 152 times 9 is 1,368 square feet. Now to figure out how many sheets that's going to take, how big is a sheet? 4 by 8, which is 32 square feet, correct? So you're just going to take that total area and divide by 32 square feet. So 1,368 divided by 32, I get 42.75. And of course, we always round up. That's going to be 43 sheets. So far, that's just the lower area. I have not done the gable ends yet. To do the gable ends, we need to find the area of that triangle. To know that, I need to know either the height or the slope. Let's say I know that the slope here is a 512 slope. What that means is for every foot of run, it rises 12 inches. How many feet of run do we have? Half of the 32 would be 16 feet. So that height if I have a run of 16 feet here, that height is going to be 16 feet times 5 inches per foot, or 80 inches. For doing sheeting, I need that converted into feet. So converted into feet, 80 over 12 reduced to a mixed number is going to be 6 2/3 feet, correct? So if this height is 6 2/3 feet, what's the area of that gable end? Well, it's 32 feet on the base times 6 2/3 feet tall divided by 2 because it's a triangle, right? Which is going to give us 0.67, and that is square feet. Now that's one end. How many? There's going to be 2 ends to this thing, so we need to multiply by 2. That's going to be 113.33 square feet. 33, 34, depending on how you round. 213, yes. I don't know why I wrote down 1. 213, thank you. And now that has to be divided by what to figure out how many sheets? 32 again. We divide that by 32. That's 13 1/3 sheets, or 14 sheets. Does that make sense? You look sheepish, Jasper. If you were framing this up with conventional rafters and not with trusses, how many studs would it take to go across there? Well, do we need a stud on each end? No. So the number of studs is going to go to 12 over our on-center spacing times the span. Then we subtract 1 because we don't need 1 on either end. If I assume my on-center spacing is 16 inches, that's going to become the number of studs equals 12 over 16 times 32 and minus 1. What's 12 16ths times 32? I get 24. Minus 1 would be 23 studs. Any questions on finding the number of studs? Here's a brain buster for you. What's the longest stud going to be? How long about? We already found this. 80 inches. I'm going to put an example up here for you guys. This here is a 30-foot by 48-foot house. It is a 612 slope. I want you to find for me external wall sheathing. That's without the gable ends. 2 gable end sheets. 3 number of studs in each end. And 4 longest stud in the gable end. You have to use the 612 to figure that out. Oh yeah, the wall height would be 9 feet. You're right. Yes. Yeah, unless you're told otherwise. Okay, you guys got that down? Let's go back to this one. The inductive reactance is 2 times 3.14 times 60 times 3. What'd you get? $1130.4. Does that look right? Yeah. What'd you get then for your total impedance? It's the square root of 1130.4 squared plus 3000 squared, right? Or the other way around. You guys get 3205.9. You might get that? Yep. What'd you get for your current? What is it? Come on, be brave. Somebody throw something out there. 0.068? It's correct, 0.0686. So that would be amps, that's 68.6 milliamps. Perfect. All of this is pretty much the same if you have a capacitive circuit. Capacitive circuit. So let's say we got a capacitive circuit here with a 5 kilo ohm resistor. And let's say we have a capacitor here that is, well, let's go 12 microfarads. A millifarad is actually a huge capacitor, usually. The capacitive reactance is XR1 over 2 times pi times the frequency times the capacitance. So that's 1 over 2 times 3.14 times 60 times 12 microfarads. Micro is times 10 to what power? -6. It's a millionth. So that would be 0.000012. This is 1 divided. You have to put that bottom in parentheses if you do this on the calculator. So 1 divided by 2 times 3.14 times 60 times 0.1234112. Close my parentheses and it equals 221.2 basically ohms is my capacitive reactance. Now the impedance, the resistance is still at 90 degrees. The capacitive reactance is at 270 degrees or down. The total resistance is found like this. You're basically filling in that rectangle, the diagonal of that rectangle. So your total reactance squared is equal to your resistance squared plus your capacitive reactance squared. Again, I often will just write it as that total reactance is equal to the square root of the resistance squared plus the capacitive reactance squared. So our resistance was what, 5? Yep, 5 k ohms. So 5,000 squared plus the 221.2 squared. So second square root 5, 1, 2, 3 squared plus my answer squared. Okay, 504.9 ohms. 5,004.9 ohms, I should say. That is my total impedance. And of course, I can find the total current the same way now, just voltage divided by impedance, right? So I want you guys to take this circuit, still going at 60 hertz. With a resistance of 3.5 kilo ohms and a capacitance of, oh, let's go 0.2 millifarads. Find capacitive reactance, total impedance, and 3 for a voltage of 110 volts. Find the total current. Got it all down? Okay. So Woods, back up to your drawing here. First of all, you have a perimeter of how much? 156 feet. So the area, the wall area, is 156 times 9, which is 1404. That's square feet. We divide that by 32. Sounds good. Yep, 43.875. So 44 sheets there. So it's 44 for this. Gable ends. I should have left myself a little more room here. We'll just fill it in here. This is 30 feet. So that means we have a run of 15 feet. Which means this height here is 15 times 612, which is 90 inches is that height. So that actually is our longest stud right there, 90 inches. The number of sheets on the gable end, I have to convert that 90 inches into feet. 90 over 12 is 7.5 feet. So that area is 30 feet times 7.5 feet divided by 2. Now, of course, it's divided by 2, but then I'm going to multiply by 2 because there's 2 ends, right? 225 works for me. Then you divide that by 32 to get 7.03. So we got to round up to 8 sheets. So 8 sheets for the gable ends. Number of studs in the gable end? Well, it's 30 feet. I didn't tell you on center, but you can assume 16. So 12 over 16 times 30 minus 1. I'm just going to do that in the calculator. 12 divided by 16 times 30 and then minus 1. It tells us 21.5. We're going to say 22 studs. Chances are only 21 is all you'd use. But generally, you put one in the middle, you get out towards the edges. Once that stud gets to be less than 16 inches in height, you usually aren't going to use it anyway. The last thing I have for you guys is let's do the ceilings. Let's say we've got a 36-foot by 50-foot house. For ceilings, we need to find the floor area. Why would we find floor area? Should be the same as the ceiling area. Unless you have vaulted ceilings would be the only difference. We're assuming flat ceilings for now. So that area is going to be 36 feet by 50 feet, otherwise known as 1,800 square feet. A sheet of sheetrock is the same size as a sheet of plywood. So we divide by 32. Giving us 56.25. Which of course will round up to 57 sheets. If you ever get into, I don't know how you guys do it out at the project house. If you ever get into some of the larger builds, they actually put up the exterior walls and then they sheet the whole ceiling, and then they'll go back and build the interior walls. Partly because then you get less cracking on the sheetrock where it meets the sidewalls. Another reason is just plain faster. You don't have to cut around the interior walls as you're sheetrocking the ceiling. But it is pretty common now. Okay, for woods, I'm going to give you guys a packet here in just a second. In fact, I'll give it to you right now. For you guys, what's that? So yeah, 0.0314. That sounds right. For you guys, it's going to be units 38 and 39 in your little book. If you want to look at unit 40, 40 goes over capacitance and inductive circuits together. RLC circuits.